Our goal is to adapt differentiation and the idea of instantaneous rate of change to functions of multiple variables. However, this turns out to be a little bit tricky. To show you what I mean, let's suppose that your altitude is given as a function of your longitude and your latitude. Let's suppose, as well, that you're standing on the side of a mountain. To help you visualize this, I'm going to give a few illustrations. The first one is a topographical map. You should think of this as us looking down on the mountain from above, with each curve representing a constant altitude. I'll also draw this from the side, as if we were watching someone climb the mountain from a distance. Let's suppose that I draw where we're standing. I'll use an X on the topographical map and a stick figure on the side view. And before we do anything, I want you to think about how the altitude will change depending on the direction in which we're traveling. For example, let's say we travel laterally around the side of the mountain. I'll try to draw this on the side view as well. In this case, we're not going to gain any altitude, right? We're traveling to the side. On the other hand, if we travel towards the peak of the mountain, like so, notice that our altitude increases as we're forced to climb the mountain. What this is saying is that the direction matters. When we travel laterally, there's no change in altitude, so we expect the derivative to be 0. But when we travel towards the peak, our altitude is increasing, and hence the derivative should be positive. For our purposes, we won't be able to describe what happens in both directions simultaneously. So, we're going to content ourselves with describing the derivative in one direction at a time. So, let's take x1 through xn to be our variables in Rn, and f to be a function on those n variables. We'll define the partial derivative of f with respect to xi at the point A as the following limit. A few things to talk about. The first is these weird curly d's. Instead of df dx, we will say df dx to indicate that this is a partial derivative. The other is that this looks like the definition of the derivative, except there are a bunch of variables that are just coming along for the ride. And importantly, this plus h term only occurs in the ith coordinate, that is, the coordinate with which we're finding the partial derivative. And what this represents is the instantaneous rate of change of the function f if we travel in the xi direction. Alright, taking this definition for a spin, let's compute the x derivative of this function at the point 1, 3. All we have to do is plug everything into our limit. So here we'll just apply the definition, then evaluate the function at these points. But this is our usual one-variable limit, so we just have to expand everything out, do some canceling, some simplification, and voila. So that wasn't too bad, but we can save ourselves a bit of time by defining the partial derivative function. All right, just like we did in single variable calculus. To do this, we compute the limit, but we leave the variables in terms of x and y instead of substituting in numbers. Let's repeat the above example, but now compute it for general x and y. We start off the exact same way, except now we've got a bunch of x's and y's hanging around, but they won't cause us too much trouble. Just treat them as though they were numbers, remembering that the limit is in h, and doing so we arrive at 2xy. And yeah, if we plug x equals 1 and y equals 3 into this, we get out 6, which is the same answer as before. You can and should check that if you do the general calculation for the y derivative, you get x squared. Seriously, pause the video and give it a shot. We've thus computed the two possible partial derivatives for the function x squared y, and this is what we got. The x partial looks like the derivative of x squared, but times y, and the y derivative looks like the derivative of y times x squared. And that's not a coincidence. The partial derivative of f with respect to xi can be computed by differentiating x sub I while holding all of the other variables constant. And yeah, we can see that in the definition. It looks like we're only differentiating x sub I and leaving everything else alone. This is going to make computing partial derivatives way easier. For example, let's find the derivative of y e to the xy. Starting with the x derivative, we're going to pretend that y is a constant, right? This means that I can take it out of the derivative computation. Differentiating e to the xy, but pretending y is a constant, thus gives us y e to the xy. The y derivative is a little bit trickier, since in this case we're going to have to use the product rule. The derivative of y is 1, while the derivative of e to the xy is x e to the xy. Factoring gives us this. So partial derivatives tell us the instantaneous rate of change in a particular direction and are computed by pretending that all the other variables are constants.